The FICO Xpress Optimizer offers the possibility of solving optimization problems with multiple objectives. To optimize several objectives sequentially, the user can add new objectives using the problem method setObjective, passing an objective index argument to indicate the multi-objective context. The model will be run for each objective sequentially, printing the log for each sequential run. The sense of the first objective defines the optimization sense for all objectives. To revert the sense of the optimization for a certain objective, you can assign the objective a negative value for the weight argument, just as in the example shown. To solve multi-objective optimization problems where several objectives are considered simultaneously, you can do so in the Python interface by using the problem.addObjective. This function adds a new objective to the problem and can also be called after an initial call to p.setObjective. When this function is called, the existing objectives will remain as part of the problem. The function can receive one or more expressions, and a set of optional arguments that include a priority value, a weight value, an absolute, and relative tolerances. Depending on the values of the priorities and weights specified by the user, Xpress Optimizer will apply different multi-objective optimization approaches. In case all objectives have the same priority but different weights, a blended or Archimedean approach will be applied where the objectives will be aggregated in a single objective function, given by the linear combination of the objective expressions times their corresponding weights. For problems where all objectives have different priorities but the same weight, a lexicographic approach will be applied. In this method, the optimizer will solve the problem for each objective separately from the highest priority to the lowest, fixing the optimal objective values in subsequent runs by adding a new constraint to the problem after each run to ensure that the optimal value is kept within the relative and absolute tolerances defined by the user. In cases where objectives have both different priorities and different weights, a combination of the two previous approaches will be applied. The solver will run a lexicographic approach by solving the problem for each priority level from highest to lowest, but in each iteration, it will optimize the linear combination of all objectives with that priority level. The following examples showcase the use of the three methodologies. In the first one, a blended approach is applied with two objectives added via two p.addObjective calls. Since the default objective sense is to minimize, we inverse the sense of the first objective to maximization by assigning it a negative weight. In the lexicographic example, an initial call to setObjective redefines the default sense to maximize returns with highest priority, which requires passing a negative weight to then minimize risk with a lower priority in a subsequent run to ensure that the optimal return is maintained when optimizing for this objective. Finally, the hybrid approach shows a combination of both cases, with the first two objectives being combined in a weighted sum manner in a first run for priority level 1, and the optimal results of this optimization run will be kept via new constraints added to the problem before maximizing it for the third objective. The Markowitz notebook example formulates a portfolio optimization problem with two objectives: maximizing the return while minimizing risk, which is defined by a nonlinear function representing the variance. After the initialization of the return and covariance data objects, the problem is created and decision variables for the fraction to allocate to each share are created. Since all objectives must be linear, we model the covariance objective via an auxiliary transfer variable, which we will aim to minimize, and an additional constraint. Then, both objectives are created and added to the problem. We explore the Pareto frontier by solving the problem multiple times for a list of weights containing 100 equally spaced values ranging from 0.05 to 0.95. For each weight combination, the two objectives are specified by passing their respective objective index and the corresponding weight. Note that by setting the first objective to be maximized, all subsequent objectives will also be treated as maximization objectives. To reverse the optimization sense for the second objective, we need to assign it a negative weight. Since in each iteration both objectives will have the same priority but different weights, a so-called blended multi-objective approach is applied, where the objective is defined by the weighted sum of all objectives. The resulting optimal values of the several runs are stored in a list that we use to plot the Pareto frontier. By running the code cells up to this point, we can observe the Pareto frontier generated from the iterative blended approach with a blue line. Next, a unique solution is found by applying a lexicographic approach to the same problem. By specifying the two objectives with a different priority level but the same weight, Xpress will solve the problem twice. After the first run, a constraint is added to ensure that the optimal value for the first objective is maintained within a relative tolerance of 10% from the solution value of the first optimization run. By running the last code cell, we can observe the Pareto frontier generated from the blended approach as a blue line, and observe that the solution from the lexicographic approach lies on this frontier, shown as a red dot.